please pause the video and try this problem. I hope you gave that a shot, and now we'll attack this problem together. First, we have to choose a problem-solving framework. The first two frameworks to choose from in your physics course are kinematics, which includes projectile motion, and Newton's second law. Well, this problem mentions mass, which fits into Newton's second law, and the problem mentions a force, which fits into Newton's second law, and the problem mentions acceleration, which fits into Newton's second law. So we're going to use the Newton's second law problem-solving framework. Now, the concept of acceleration would also fit into a kinematics framework, but there are no other concepts in the problem that fit easily into kinematics, so it looks like we'll just focus on the Newton's second law framework. Now, you've probably noticed already that this problem deals with what's called in physics an inclined plane. We're going to treat this hill as an inclined plane. So you might have thought that we should say that we're going to use an inclined plane problem-solving framework. But that would be a mistaken way to think about it. You shouldn't think about it in that way. There is no inclined plane problem-solving framework. Instead, what we have to realize is that we can solve inclined plane problems using the same Newton's second law framework that we've already demonstrated in the previous videos. Inclined planes are not really a special type of problem. At least they don't have a special type of method. Inclined plane problems are solved simply by adapting the Newton's second law framework that we've already demonstrated. So in the rest of this solution, we will try to illustrate that we can solve this inclined plane problem simply by adapting the Newton's second law framework that we've already been introduced to. We should not think of inclined plane problems as requiring a separate problem-solving framework. They're just an application of Newton's second law. Here's our systematic method for Newton's second law problems, which I hope you have printed out. Make sure we have a sketch. We were already given the sketch, but let's add the velocity vector to this sketch. The direction of the velocity vector should indicate the object's direction of motion, and the problem says that the mass is sliding down the hill. So we know that the direction of motion and the direction of the velocity vector should be pointing down the hill. Now I've drawn the vector, and we need to label that vector. Here's a good label for that velocity vector. So we were already given a sketch, and we added the velocity vector to the sketch. We want to identify the question with a question mark and a symbol. Well, right now we're working on part A. The question asks for the magnitude of the normal force, and a good symbol for that would be a lowercase n without the arrow. Remember that with the arrow, it would indicate the complete normal force, including direction. The symbol without the arrow means the magnitude. Symbol without the arrow means the magnitude. Always try to use the exact right symbol. But also notice we need to find the direction of the normal force. Here we should include the arrow because a magnitude doesn't have a direction. Only the complete vector has a direction. So I encourage you to actually write down question marks to help you identify symbols or words in a symbol for exactly what the question is asking. So we've completed this step. We need to check that the units are SI units. Kilograms are SI units for mass. Those are the only units it looks like we need to check. So we checked the units. This step is not relevant because this step is for symbolic problems, and we're working on a numeric problem. Now we can shift to free body diagram phase. Identify the object we're going to apply Newton's second law to. Usually that's the object whose mass was mentioned, and the object here whose mass was mentioned is just called the mass. Oh, actually, let's see, is there an inconsistency in how I wrote the question here? Okay, well, I fixed that inconsistency. Now all the parts of the problem refer to the object as a mass. So the object that we're going to focus on is that mass. during the interval of time that it is sliding down the hill. The object we will apply Newton's second law to is the mass during the interval of time that it's sliding down the hill. Now we need to start a free body diagram for the object. For which object? For the object we just identified, the mass. Remember that you should have the problems document printed out so that you can keep this problem in front of you, even when I push it off the screen. And remember that if you find that this video explanation is moving too slowly, you could rely on the solutions document as a supplement or replacement to the video explanation. So now let's start our free body diagram. I encourage you to label exactly who you're going to include in the free body diagram. We're going to include all the forces on the mass. This dot represents the mass. Now remember, we want to start the diagram with a vector for the object's weight. Now, what's the direction of the object's weight? Well, you should know there is a simple rule for identifying the direction of the object's weight, which I hope you have memorized. We've talked about that on this handout. The direction of the weight force is down. So we're going to draw down as the direction. The direction of the weight force is down. Make sure you include a label for that vector. Here's the label to show that that is the weight force. Some students get confused here because this is an inclined plane problem. Some students might think that for an inclined plane problem, some people might think that because this is on an inclined plane, they have to handle the weight differently than usual. Well, you can see that's just not true. The fact that this is an inclined plane problem has no effect on the direction of the weight. Just memorize this simple rule. There's a simple rule for the direction of the weight force. The direction of the weight force is down. The fact that this is an inclined plane problem has no impact on that direction. I think that should make sense. Remember that the weight force is the gravitational force exerted by the Earth on the object, and I think it matches common sense that the Earth's gravity is a downward pulling force. So we've completed this step. We started the free body diagram by drawing the vector for the object's weight. Now we continue the free body diagram by identifying the things that are touching the object. What's touching this mass? Well, the hill is touching the mass, and so the hill can exert a force, and I hope that you recognize that the hill fits into the class of things that we would consider a surface. So that means that the hill is going to exert a normal force. The hill will exert a normal force on the mass. I haven't really given you a definition of what surfaces are that exert normal forces, but I hope this list in the handout gives you a feel for the things that we treat as surfaces. Notice that something I specifically mentioned is that inclined planes are treated as surfaces, and I hope you can see that the hill in this problem is basically an example of an inclined plane. So the hill inclined plane will exert a normal force. What's the direction of the normal force? Well, remember there's a simple rule that you should have memorized for the direction of the normal force. The direction of the normal force is perpendicular to and away from the surface that is touching the object. Well, perpendicular to and away from this surface would point in this direction, right? So that's the direction of our normal force. We need to add that to the free body diagram. Here's the vector showing the direction of the normal force. We need to label that vector. Always label your vector arrows. And notice that in order to correctly show the direction of the normal force, we had to include these dashed reference lines to show the angle made by the hill, the inclined plane. I'm drawing these as dashed lines to show that they don't represent forces in the free body diagram. They're just included so we can correctly show the directions of the actual forces. Notice how this normal force now is pointing perpendicular to and away from the surface of this dashed line that would touch the mass. When you tried this problem on your own, did you get the direction of the normal force correct? Remember, do not assume that the normal force points up. There are many problems where the normal force does point up, like the previous problems in this video series. But there's also many problems, like the problem we're working on right now, in which the normal force does not point up. So just apply the rule. The rule is that the direction of the normal force is perpendicular to and away from the surface that is touching the object. Remember that in mathematics, normal means perpendicular, and that helps us to remember the correct rule for applying the normal force. Remember that it's important to include this type of reference line in your free body diagram, even though it doesn't represent a force, just so you can show the correct direction of the forces that we are drawing. Now, anytime there's a normal force, it could possibly be accompanied by a frictional force. So we should check for that, but we know there's no friction in this problem because the problem told us there was no friction. So what do we do now to identify further forces? Well, remember, we simply have to ask ourselves, is there anything else that is touching the object? Is anything else touching the mass? And I don't think there is. I don't think there's anything touching this mass besides the hill. Therefore, there are no other forces on the object. So I think we finished the free body diagram. Remember to try to keep a neat, clean, free body diagram. Remember, there's a simple two-step process for the free body diagram. First, you draw the vector for the object's weight, and then you draw force vectors for the things that are touching the object. And remember that there are simple rules that you need to have memorized for finding the directions of some forces, such as the weight and the normal force. Those are on this handout. One simple rule and another simple rule. So now we can move on to our next phase, the force table phase. Now is a good time to choose our axes. And remember, you should usually have an axis that points in the object's direction of motion. Well, we've seen that this object is sliding down the inclined plane, so we should have an axis that's pointing parallel to and down the inclined plane. Okay, so here I've drawn those axes. All axes arrows should be labeled. So let's label these as X and Y. So I've chosen a positive direction pointing in the object's direction of motions, down and parallel to the inclined plane. And it's conventional to choose an axis that's parallel. It's conventional when an axis is parallel to the inclined plane. It's conventional to call that the x-axis. Then the y-axis has to be perpendicular to that, and the conventional direction for a y-axis for this type of inclined plane problem is perpendicular to and away from the inclined plane. So that's how we drew it. Don't assume that your axes should be horizontal and vertical. There are many problems, such as the problems previously in this video series, where the axes should be horizontal and vertical. But there's also many problems where the axes should be slanted, such as this problem that we're working on right now, where we've drawn, so to speak, slanted axes. Just use the rule that it's usually best to choose an axis that points in the object's direction of motion. All right, make sure that you actually write down on your paper your axes. Okay, now we're ready to start our force table. Here's the setup for our force table. We've seen that the first row of the force table is for the magnitudes of the overall vectors, and the next two rows are for the components. Remember to always try to use the exact right symbols. These are the correct symbols for components. These are the correct symbols for magnitudes of the overall vectors. We don't write these with arrows because then they wouldn't stand for magnitudes. We write these symbols with arrows because the purpose of the free body diagram is to show the directions, and only the complete vector has a direction. Try to make an effort to always use the exact right symbol. That will gradually strengthen your physics skills. All right, so let's start with the weight force. Well, we're not given a number for the weight force, but we need to know there is a special formula for figuring out the magnitude of the weight force. So let's work that out off to the side. So we'd have that special formula is W equals mg. The number for the mass here is 9 kilograms. And our g, the magnitude of the acceleration due to the Earth's gravity, is 9.8 meters per second squared. 9 times 9.8. So that'll give us 88.2. Now that we've solved to a single number, we should put in the SI units. Weight is a force, so it has the SI units of force, which are newtons. So we've worked that out, and now we can write that down here. Notice that we do all of our work off to the side, not in the main force table, because we want to keep the force table clean. First, we write the general formula, then we plug in. Now, of course, this is the same approach we used for the magnitude of the overall weight force in each of the previous problems. Maybe some students might think that because this is an inclined plane problem, we can no longer use this formula. But nope. It doesn't matter whether you're working on an inclined plane problem or not. There is a special formula for figuring out the magnitude of the weight, and that special formula is W equals mg. This special formula works just as well for inclined plane problems as it does for any other type of problem. Now we need to break this weight force into x and y components. Now notice that that will be a little difficult on this problem, because this weight force is neither parallel nor anti-parallel to either axis. Since the weight force is neither parallel nor anti-parallel to either axis, that's the situation where you have to draw a right triangle in order to break the weight force into components. So we're going to have to draw a right triangle in order to break this weight force into components. We need that right triangle approach because the weight force is neither parallel nor anti-parallel to either of the axes we chose on this problem. And remember, we're not going to put that right triangle in the main free body diagram because that would make this sketch too messy. Let's draw a separate sketch with the right triangle that we'll use to break the weight force into components. So now I've drawn a separate sketch, including just the vector for the weight force and a reference line to show the angle of the inclined plane. And I've included the axes, and now we have to draw the right triangle using this method that I think we saw in the previous videos. So remember that the overall vector should represent the hypotenuse of the right triangle. So this side here, this arrow, will represent the hypotenuse of our right triangle. And we should draw one of the legs parallel to the x-axis. So through this point, in the tail of the overall vector, I'm going to draw a line parallel to the x-axis. That'll just overlap with the dashed line. So here, through the tail of the overall vector, I've drawn a line parallel to the x-axis. And now we should draw the other leg parallel to the y-axis. So through this point, in the head of the overall vector, I'm going to draw a line parallel to the y-axis. So through the head of the overall vector, I've drawn this line parallel to the y-axis. So do you see how we accomplished what we wanted to? We've ended up with a right triangle where the overall w vector represents the hypotenuse. This is the hypotenuse because it's opposite to the 90-degree angle. One leg of the triangle is parallel to the x-axis. That's this leg here, parallel to the x-axis. And one leg is parallel to the y-axis. This leg here is parallel to the y-axis. Do you see why this has to be a right angle? Remember, this line is parallel to the x-axis, and this line is parallel to the y-axis. But the axes are perpendicular to each other, and therefore these two lines are perpendicular, and this is a right angle, which is good, because we were trying to draw a right triangle. So this is the correct method. If this gave you difficulty, you should memorize this method. My experience is that almost all students are unable to draw the correct right triangle the first time they try an inclined plane problem. Very few students are able to come up with this right triangle correctly because most students assume that the legs of the triangle will be horizontal and vertical. So most students would try to draw a right triangle that looks like this. Most students try to draw a right triangle that looks like this, simply because this is what they've seen on previous problems. But I hope you can see that this does not match the rules for coming up with the right triangle. So this would be wrong. This is the common student mistake. Do not assume that the legs of your right triangle would be horizontal and vertical. That's the common student mistake. There are many problems where the legs will be horizontal and vertical, like the previous problems in this series. But there's also many problems, like an inclined plane problem usually, where the legs are not horizontal and vertical. So just use this rule. You should draw the legs of the right triangle parallel or anti-parallel to the axes. That's the rule that we applied in this case. You can see this is wrong because the legs of this triangle are not parallel to the axes. Also, you can see this is wrong because remember the overall vector is supposed to represent the hypotenuse. But in this triangle, the overall vector would be a leg, not the hypotenuse. That's another way to see that this is wrong. This is a difficult triangle for students to draw because it feels weird for the hypotenuse to be vertical. Students are not used to seeing a vertical hypotenuse, but we just have to get used to that. There's actually quite a few cases in physics where we'll end up drawing a right triangle like this with a vertical hypotenuse and slanted legs. From the previous problems, you're used to having a slanted hypotenuse and vertical and horizontal legs. But on many inclined plane problems, instead you'll need to have a vertical hypotenuse and slanted legs. It's all based on following this rule. Were you able to get this right triangle correct? Like I said, most students are not the first time they try it. All right, so now let's continue. Now we have to put arrows on these legs. We need to put arrows on these legs because the components are vectors with their own directions. So how can we figure out the directions? Well, one approach you could use is remember that the components represent the overall vector. Since the overall vector points down, each of the components should also point down. This component points down and to the right, and this component points down and to the left, but they're both pointing partially down to represent the overall vector, which is pointing down. Here's a more formal rule for figuring out the directions of the components, again based on the idea that the components represent the overall vector. So where we have the head of the overall vector, that should be also overlapping with the head of the component, as we have here. And where we have the tail of the overall vector, that should be overlapping with the tail of the component, as we have here, and therefore this is the head of this component. So we went through two different ways to figure out the directions on those arrows. Now remember, every vector arrow needs a label, so we need to step in and show that this is w sub x, this side is w sub x, and this side is w sub y. How do I know those are the right labels? Well, remember, this side was the one that was parallel to the x-axis, so it's the x component. And this side is the side that, as it turns out, is anti-parallel to the y-axis, so it turns out to be the y component. And now is a good time to figure out the signs on the components. Remember, you should try to figure out the signs on the components before the magnitudes, so that you don't forget about the signs. Well, w sub x is pointing parallel to our x-axis, which is the positive direction. So we can say that this component is positive. Now w sub y is pointing anti-parallel to the y-axis, which is our negative direction, so we can say that w sub y is negative. Do you understand what I mean by that word anti-parallel? Anti-parallel means that w sub y and the y-axis are pointing in opposite directions. Parallel means that w sub x and the x-axis are pointing in the same direction. So here's a good right triangle for breaking the weight force into components. Now actually there's two right triangles. There's two different right triangles we could use to break this weight force into components. You only need one of them, so it would be perfectly okay just to use this right triangle. You don't need to draw both right triangles, but just for practice and just so that you can get a better understanding of this method, I'm now going to draw the alternative right triangle, just so that you can see both approaches and so that you get a better feel for these rules. So you only need one right triangle to break a vector into components, so now you could proceed to the next step of the analysis. But for practice, I'm going to show you the other right triangle here, so we get a better understanding of these rules for drawing the right triangle. How do we draw the other right triangle? Well, notice that in this case, I drew a line parallel to the x-axis through the tail of the overall vector. And I drew a line parallel to the y-axis through the head of the overall vector. Well, we can just flip that. We could draw the line parallel to the y-axis through the tail of the overall vector. And we could draw the line parallel to the x-axis through the head of the overall vector, and that will give us the alternative right triangle. So here's a fresh diagram, and as I said, for practice, let's draw the alternative way to come up with the correct right triangle. Well, now through the tail of the overall vector, I'm going to draw a line that's parallel to the y-axis. Through this point, I'll draw a line parallel to the y-axis. So here's a line through the tail of the overall vector, which is parallel to the y-axis. And now through the head of the overall vector, I'm going to draw a line that's parallel to the x-axis. Through this point, I'll draw a line parallel to the x-axis. Through this point, I drew a line parallel to the x-axis. Now I can just clean up the sketch a little bit. So I hope you can see now what I meant when I said that there are two perfectly good right triangles that we can draw on the same overall vector. We could draw a right triangle to the right of the overall vector, or also it would be perfectly fine to draw the right triangle to the left of the overall vector. Either of these is perfectly fine. On a real problem, you only have to draw one of these, but for practice on this problem, I'm showing you both. Put arrows on these components. Well, the overall vector points down, so our components should point down. Each of the components points partially down to represent the downward overall vector. Or we can use this more formal rule, where we have the head of the overall vector. That should also be where we have the head of this component. And where we have the tail of this overall vector, that should also be where we have the tail of this component, so the head of this component is over here. Make sure you label the components. This component here will be w sub y, because this side is anti-parallel to the y-axis. And here this component should be labeled as w sub x, because this side is parallel to the x-axis. Whereas this side was anti-parallel to the y-axis. That's how we label the components. Now we can put in the signs on the components. Remember, you should figure out the signs before you figure out the magnitudes. The x component points in the same direction as the x-axis, so the x component is positive. And the y component points anti-parallel, opposite to the positive y-axis, so our y component is negative. Of course, we've come out with the same results for this triangle, as you always would. Again, on a real problem, you only need to draw one of these two right triangles, but we're showing both here for practice so you can get a deeper insight into this method. All right, so I hope now you're understanding this method of how to draw the right triangle. Again, we ended up with a right triangle where the overall vector represents the hypotenuse. Here we have a vertical overall vector that represents the hypotenuse. And we ended up with one leg parallel to the x-axis, that was this one, and one leg anti-parallel to the y-axis, that was this one. These are the two right triangles you could end up with, either a right triangle to the right of the main vector or a right triangle to the left of the overall vector. So here's the two possible right triangles. For a real problem, you would only have to use one or the other of these, one of them, but I'm going to demonstrate the solution with both for practice. All right, now here's the next step that a lot of students don't realize they need to do. We can't make any further progress until we figure out some of the angles inside this triangle. Most students here now try to use this angle. Most students try to use this angle as the basis for their SOH CAH TOA equations, but that doesn't make sense because this angle is not in the right triangle. We're not ready for SOH CAH TOA yet because we don't know any of the angles inside the right triangle. So what we need to do is we need to figure out the angles inside the right triangle using this angle. That's going to just involve some high school level geometry. Do you know how to do that? You might want to pause the video and see if you can use high school geometry to figure out the angles inside this right triangle and or inside this right triangle. I hope you actually gave that a shot. Did you pause the video and try to use geometry to figure out those angles? That would be excellent practice. Okay. Well, there's more than one way to attack this. I'll start with this triangle, but I think the easiest approach is I'm going to extend this horizontal line horizontally like so. And I'm going to extend this vertical line vertically like so. So do you see now we have a big right triangle? Now, the purpose of extending these lines is to create a right triangle. Do you see the large right triangle that we've created? So I've outlined in red the the large right triangle that we've created. All right, and now you can see this is a right triangle because this is a right angle. So now we should be able to figure out this angle here. We should now be able to work out this angle. Can you see what this is? It's easier to think this through if we give names to all the angles. So I'll call this angle theta and this angle alpha. And do you see that theta plus alpha should equal 90 degrees? So here I used the rule that the acute angles in a right triangle add up to 90 degrees. Do you know what I mean by acute? These are acute means less than 90. So obviously this angle of the right triangle is 90 degrees. The acute angles are the two angles that are less than 90 degrees. I think that all students know that if you add all three angles, they add up to 180. Everyone knows that if you add all three angles, they add up to 180. But we know that this angle in the right triangle is 90 degrees, so doesn't that mean that the other two angles have to also add up to 90, so that all three will be 180? Okay, so this is the easiest way to proceed here. Now we know that theta is, what the angle we're calling theta is 35 degrees. So I think we can see that alpha is going to be 90 minus 35. This angle will be 90 minus 35. 90 minus 35 degrees is 55 degrees. And you can see now that all the angles together in the right triangle do add up to 180. 55 plus 35 is 90, and another 90 would be 180. So it should make sense that the acute angles in the right triangle add up to 90 degrees. Now you can see why it was a good idea to remember that we had to extend this line down and extend this line across in order to create this right triangle. This right triangle didn't exist in our original picture. That big right triangle didn't exist in the original picture. We had to extend this line down and this line across to make that right triangle, and you can see that was a good idea because it allowed us to use this rule and figure out this angle inside the right triangle. All right, technically we could stop there. Technically we only need one angle inside the right triangle, but it's actually conventional to go on and figure out this angle. So let's go on and figure out this angle as well. You might want to pause the video and see if you can figure out that angle. By the way, notice whenever you figure something out in geometry, you need to add it to your sketch. We figured this angle, so we wrote it down in the sketch. And notice that it was easier to think through the logic because we gave names to these angles, alpha and theta. All right, now to figure out this angle, we should focus on this smaller right triangle. So now I've outlined the new right triangle that we're focusing on, this one outlined here in blue. Of course, this is the right triangle that we created. We created this right triangle in order to show the components. We know that it's a right triangle because we know that this is a right angle. This was created to be a right angle because these two sides are parallel to the axes, and the axes are perpendicular to each other. So we'd like to figure out this angle, and to help us do that, we should give the angle a name. So I called this angle beta. Obviously, you don't want to give it the same name as the previous angles because we want to distinguish them. And I think it should be obvious to you, I hope it's obvious, that alpha plus beta is 90 degrees. And here we're using the idea again that the acute angles in a right triangle add up to 90 degrees. So this angle plus this angle in the small right triangle outlined in blue, that should add up to 90 degrees. Now we know that alpha is 55 degrees. So it should be easy to see that beta is 90 minus 55. And we should add that to our sketch. Beta is 90 minus 55. 90 minus 55 is 35, so we've added that to the sketch. So now we've accomplished our goal. We've figured out the angles inside this right triangle that represents the components. using this idea that the acute angles in a right triangle add up to 90 degrees. And again, notice if these add up to 90 and then you add this 90, you would get to 180, which matches what you know about right triangles. If this geometry was easy and obvious for you, then you wouldn't have to write out the steps so painstakingly. But I'm going to go through the steps slowly and carefully just to help people that might find this geometry to be difficult. So remember that the key was extending this line down and extending this line across so that we got this large right triangle. That's what allowed us to say that alpha plus theta was 90 degrees. Were you able to work this out? Were you able to use geometry to work out these angles in this triangle? If not, how could you have done better? One piece of advice I would definitely give you for working on geometry is make your sketch as large as possible. The larger the sketch is, the easier it is to think about it and work with it. If your sketch is really small, then it's very difficult to see the various details, and it's hard to fit in each piece of information that we need to fit in, like each of these angles. So try to make as large a sketch as is practical so that you can clearly identify each separate part of the sketch, and so that you can build in each new piece of information that you'd like to build in to the sketch. So that's my advice. That's one piece of advice for improving your geometry skills. Make clear, clean, large sketches. And every time you figure something out, build that extra information into your sketch. Again, the other key for the geometry here was extending this line down and extending this line across so that we formed this new right triangle, and using the idea that the acute angles in the right triangle add up to 90 degrees. I think it also helped that we gave names to each angle, so that we didn't have to call any of the angles it. We could refer to each angle clearly by a name or a symbol. All right, now we could proceed to SOH CAH TOA. Now we know the angles inside the right triangle, so we could proceed to SOH CAH TOA. But just for practice, let's practice the geometry that allows us to figure out the angles in this right triangle. You don't need to do this. You only need one right triangle to finish the problem. But for practice, we'll build our geometry skills if we also try to figure out the angles in this right triangle. So again, why don't you pause the video? Why don't you pause the video and see if you can use geometry to figure out the angles in this right triangle? Well, first we will use the same trick. We'll use the same trick that we used over here. We need to extend this line across and extend this line down to make a large right triangle. Okay, so now by extending those lines across, we've created a large right triangle, which I've outlined in red. This is the same right triangle as we got over here in red. So again, we can call this angle theta and this angle alpha, and we'll know that theta plus alpha equals 90 degrees, because the acute angles in a right triangle add up to 90 degrees. Theta is 35 degrees. So that tells us that alpha is 90 minus 35. So we know that alpha is 55 degrees, and we should add that to our sketch. Alpha is 90 minus 35, which is 55 degrees. So far, the logic on this side is exactly the same as the logic that we used to find alpha on this side. Now, notice that this angle of 55 degrees, this isn't one of the angles that we directly need. We need the angles inside this small right triangle. Finding this 55-degree angle is just a helpful step, but we still wrote this down in the picture. That's the way you do geometry. In geometry, you figure out every little thing you can, even if it doesn't directly answer what you ultimately need. And every little thing you figure out, you should write down immediately in your sketch. So we wrote this down in our sketch as one little step that might be helpful. Now, the next thing that we could do, there's more than one way we could proceed here, but one way we could proceed now is by finding this angle. It always helps to give a name to the angle that you're thinking about, so I'm going to call this gamma. Remember that in physics, you want to avoid using the word it. So rather than saying that, so we want to have a name or a label for everything that we're trying to talk about. So rather than saying that it's 35 degrees or it's 55 degrees, we want to figure out this thing, it's better to say that theta is 35 degrees, alpha is 55 degrees, and now we're trying to find gamma. All right, now the way to figure that out is to understand how big this angle is from here to here. I tried to outline that in green. Can you say how big is this angle from here to here? This is one of the trickiest steps in the logic. Well, keep in mind that the dashed line here is parallel to the x-axis, and this line for w sub y is parallel to the y-axis. But the two axes are perpendicular to each other. Therefore, w sub y is perpendicular to this dashed line. And if they're perpendicular, that means that this angle from here to here is 90 degrees. From here to here is 90 degrees. Did you follow that logic? I'll go through that one more time. The x-axis is drawn to be parallel to the dashed line, and w sub y is drawn to be parallel to the y-axis. And the axes are perpendicular to each other. The axes are perpendicular to each other. That means that the dashed line is perpendicular to w sub y. And that means that they form a 90-degree angle. I think that's the most difficult step of geometry in dealing with this material. Okay, but now our next step should be straightforward. If the angle from here to here is 90, then we know that alpha plus gamma is 90 degrees. Alpha plus gamma is 90, and alpha we know is 55 degrees. So gamma is 90 minus 55, which is 35 degrees. And every time you figure something out, make sure you add it to your sketch. 35 plus 55 is 90 degrees. Again, that logic one more time is that the w sub y line is parallel to the y-axis, the dashed line is parallel to the x-axis, the two axes are perpendicular to each other, and that means the w sub y line is perpendicular to the dashed line, and that means this angle is 90 degrees. All right, I think that's the most difficult step of the geometry for dealing with these issues. So now we've succeeded in figuring out an angle inside of this small right triangle. And this is the angle that we're going to use for SOH CAH TOA. We'll use this gamma 35-degree angle for SOH CAH TOA. So technically, we don't really need to figure out what this angle is. But just for completeness, even though we don't need it, for completeness, let's go ahead and figure out this other angle in the small right triangle. Okay, so I've given a name to this angle that we're trying to figure out. Let's call this angle delta. Notice we want to give different names to different angles. So I'm making up some new symbols since this is not exactly the same angle that we've focused on earlier. And to figure out this angle, we should focus on the fact that this is a right triangle. So now we're going to focus on this small right triangle that I've outlined in orange. This is the right triangle that we drew in order to represent the components. And now things should be pretty straightforward. Remember that the acute angles in a right triangle add up to 90 degrees. That means that gamma plus delta should add up to 90 degrees. And we know that our gamma we figured out is 35 degrees. So clearly delta will be 90 minus 35. And every time we figure something out, we should draw that in the sketch. So we can draw in here delta is 90 minus 35, which is another 55-degree angle. All right, so we added that to the sketch. And clearly 55 plus 35 is 90. And then if you add this other 90-degree angle over here, you'll get up to 180. Remember, we know that this is a right triangle because we drew it to be a right triangle. We designed this to be a right triangle. This is the right triangle that we're using to break the w vector into components. We drew the legs to be parallel to the axes, and therefore the legs are perpendicular to each other, just like the axes are perpendicular to each other. So that's our little right triangle, and that allows us to figure out that this is 55 degrees. I'm not actually going to use this angle for SOH-CAH-TOA. I'm going to use this angle, but we just worked this out for completeness to get a little bit more practice with the geometry. Were you able to work out that geometry on your own? One of the keys here, if you're having difficulty, is drawing a large sketch. If your sketch is small, then you can't fit all the information that you need to fit into the sketch. So when you're working on geometry in physics or in any context, always try to make your sketch as large as it will possibly fit in the space that you have. The larger the sketch, the better, because it makes the sketch clearer and gives you more room to fit in all the details. If the sketch was too small, it would be hard to clearly label all the little angles that we're working with here. So one of the keys to improving your geometry skills is drawing a large sketch. Another key is figure out one little thing at a time, even if it's not what you ultimately care about. And every time you figure out one little thing, write it down in your sketch immediately, and then try to figure out one more little thing and write that down in the sketch until eventually, hopefully, you figure out the information that you need. Remember that the most important step for both of these cases here was extending these lines for the right triangle. Remember that originally we didn't have the large right triangle. We had to extend this line down and extend this line across in order to get this big right triangle, and that's what allowed us to figure out this angle alpha in both of these cases. Remember, it's also helpful in geometry to give a name to the angle that you're focusing on. That helps you to think more clearly about what issue you're dealing with at each point. And like I said, some students might not have been familiar with the idea that the two acute angles in a right triangle add up to 90 degrees. Everyone knows that if you add up all three angles, that adds up to 180, but not everyone realizes that in a right triangle, that means that the two small angles add up to 90 degrees. That's a real helpful rule to be familiar with in your physics course. That if you were doing this problem on your own, you would only have to have done one of these two right triangles. You could just have done this right triangle, or you could just have done this right triangle. I'm only covering both of them in this video for completeness and to help us practice and deepen our skills. Now the next step is to figure out the magnitudes of the components using the SOH-CAH-TOA equations. So we have to label which side is the hypotenuse, which side is opposite, and which side is adjacent. Maybe you should pause the video and try that now. Well, remember the hypotenuse is opposite to the 90-degree angle. So this side will be our hypotenuse opposite to our 90-degree angle. This side is the hypotenuse because it's opposite to the 90-degree angle. And again, over here, this side is the hypotenuse because it's opposite to the 90-degree angle. You might not be used to seeing a vertical hypotenuse, but this is the hypotenuse, even though it's vertical, because it's opposite to the 90-degree angle. We could add some information now to our sketch. Remember that we know that the magnitude of the overall weight is 88.2 newtons. Magnitude of the overall weight is 88.2 newtons, as we discovered earlier. So we should be building that into our sketch. Here I'm using the symbol without an arrow because I'm just writing down the magnitude. And with the symbol without the arrow represents the magnitude, which represents the length of that arrow. But which side is opposite and which side should get labeled as adjacent? Well, it's crucial for us to understand that who is opposite and who is adjacent depends on which angle we choose to focus on. Are we going to focus on the 35-degree angle in the right triangle, or are we going to focus on the 55-degree angle in the right triangle? Now that's completely your choice. Either choice is okay, but the convention is to use the angle that matches the angle we were given. We were given this angle of 35 degrees, so the convention is that we're going to focus on the 35-degree angle in the right triangle. So I'll follow that convention, and I'll make an asterisk here to show that we're going to focus on this 35-degree angle. And similarly, in this triangle, the convention would be to focus on the 35-degree angle, because that matches the angle we were given of 35 degrees. So I'll use an asterisk to say that in this right triangle, this is the angle that we're going to focus on. All right, and now we can label who is opposite and who is adjacent. So this side should get labeled as adjacent because it's adjacent to the 35-degree angle that we chose to focus on. And this side should get labeled as opposite because it's opposite to the 35-degree angle that we chose to focus on. That's why it's helpful to put in the asterisk. So over here, this side should get labeled as adjacent because it's adjacent to the 35-degree angle that we chose to focus on. And this side should get labeled as opposite because it's opposite to the 35-degree angle that we chose to focus on. So which side is opposite and which side is adjacent depends on which of the two angles you choose to focus on. It's helpful to put in an asterisk to indicate which angle you're focusing on. My experience is that most students that try this problem don't even realize that they need to figure out the angles inside the right triangle. Most students that try this problem, they just try to use this angle. My experience is that most students that try this problem just try to use this angle, but you can see this is completely inadequate because this is not an angle inside the right triangle that we're using for the components. So if you're going to do this with understanding, with a reliable method, you absolutely have to do the geometry to figure out the angles inside the right triangle. Otherwise, you can't decide which angle you're focusing on and who should be labeled as opposite and adjacent. Okay, so now we can write our SOH-CAH equations. So we know that sine of 35 degrees is the length of the opposite side over the length of the hypotenuse. So, and cosine of 35 degrees is the length of the adjacent side over the length of the hypotenuse, CAH. Notice that I'm writing 35 here. I'm not writing 55 because we chose to focus on the 35. We chose to focus on the 35-degree angle in the triangle, not the 55-degree. The opposite side here would be represented by the magnitude of Wx. The hypotenuse we've seen is the 88.2 newtons. The adjacent side here is the magnitude of W sub y. And the hypotenuse is the 88.2 newtons. Notice that it doesn't matter which of these two right triangles you use. You could use either of these two right triangles. We're just showing both for completeness. The opposite in both of them is the magnitude of W sub x, and the adjacent in both triangles is the magnitude of W sub y. So you could use either of these two right triangles. On a real problem, you don't need to draw both of them. Okay, so now we've set these up, and again, we could not have set up the SOH-CAH TOA equations correctly unless we'd done all the previous work, unless we had drawn a right triangle and figured out the angles and used geometry to figure out the angles inside the right triangle and decided what angle we're focusing on and labeled hypotenuse, opposite, and adjacent sides. Without all that preliminary work, there's no reliable way to write your SOH-CAH TOA equations. All right, and now we can use algebra to solve these equations. We'll multiply both sides by 88.2. To get rid of this denominator and get the variable by itself. Same for the other equation. So we need to do the calculation 88.2 times the sine of 35 degrees. Make sure you're in degrees mode. And 88.2 times the cosine of 35 degrees. So I'll round this off to 50.6 since this digit is an 8. Now that we have a single number, we should put in the units, which are newtons. And the W sub y I'll round off to 72.2. All right, now remember that we are using absolute value signs in the SOH-CAH equations because these are supposed to represent lengths of the sides. Lengths can never be negative, so we don't want to use the component symbols because a component could be negative. We want to use absolute value signs to show that we're talking about magnitudes. Magnitudes are the right way to measure a length because lengths can never be negative. So the point is, we use the absolute value signs to remind ourselves that these SOH-CAH equations do not tell us the plus or minus signs on the components. We need to go through a separate step. There needs to be a separate step where we identify the plus or minus signs on the components. We actually already completed that step, didn't we? We already saw that our W sub x is positive. And we already determined that our W sub y is negative. So this is the step where we stick in that negative sign. So that's a very important step. If we leave out this negative sign on W sub y, we're going to plug the wrong number into our Newton's second law equations, and we're going to get the wrong answer to the problem. If we make that one little mistake, our work will be useless. So it's crucial to get this correct negative sign. Remember, as I've recommended in the past, I recommend that you include a plus sign in front of your positive components because I think that will help you to remember to put the negative signs, these crucial negative signs, in front of the negative components. So this is quite important. We use absolute value signs in our SOH-CAH equations to remind ourselves that the SOH-CAH equations do not determine the plus or minus signs on the components. Therefore, we need to determine the plus or minus signs ourselves in a separate step, just like we did here. We determined the plus or minus signs from the arrows on the components, and then we added those plus or minus signs in a separate step. Your professor and maybe your textbook might not use absolute value signs in their SOH-CAH equations, but as a beginner, I recommend that you should use those absolute value signs to remind yourself that you're going to need to figure out the plus and the minus sign in a separate step. In this step, I use absolute values to show that I haven't worked out the plus or minus signs yet. These are just the magnitudes of the components. Then in this line, I write the W sub x and W sub y without the absolute values to show that now we're writing the complete components, including the plus or minus signs. Make a strong effort to always use the exact right symbol, including one symbol for magnitudes and a separate symbol for the complete components. Do not assume when you're breaking vectors into components that you will use cosine to find the x component and sine to find the y component. On many problems, you will use cosine for x and sine for y, such as the previous problems in this video series. In the previous problems in this video series, we used cosine for x and sine for the y component. But on many other problems, you will use cosine to find the y component and sine to find the x component, such as this problem that we just worked on. On this problem, we used cosine for the y component, and we used sine for the x component. So you can't make an assumption either way about whether you're going to use cosine or sine for the x or the y components. It varies on different problems. So how do you determine what to do? Just go through the steps of the SOH-CAH process to determine what the correct approach is for each individual problem. So go through this whole process. Draw the right triangle, find the angles in the triangle, decide what angle you're going to focus on, label the hypotenuse, opposite, and adjacent sides, set up the SOH-CAH equations, and then use the algebra to determine what the correct approach is, rather than making an assumption that might not apply for the problem that you're working on. Now let's check if these results make sense by building them back into our triangles. So I took our results for w sub x and w sub y and built them back into the sketches so we can check if these results make sense. We should see that the longest sides of the right triangle is the hypotenuse, and that checks out in this case because the hypotenuse is 88.2 newtons, and that's longer than the two legs of 50.6 and 72.2. The hypotenuse is the longest side in these triangles. And then to compare the legs, we should check whether the longer leg is opposite the bigger angle. Well, yes, we can see that this bigger angle of 55 degrees is opposite the longer leg of 72.2 newtons, and the smaller angle of 35 degrees is opposite this smaller leg of 50.6 newtons. The smaller angle of 35 degrees is opposite the shorter leg of 50.6 newtons, and the bigger angle of 55 degrees is opposite the bigger leg of 72.2 newtons. So that also checks out. So it does seem like we did those things check out. Now that all assumes that we did the correct geometry. We did the geometry correctly to find the angles in the first place. But based on that, we've checked that our components make sense. Okay, well, definitely the most challenging part of this of an inclined plane problem for most students for this type of problem is breaking the vector into components. So I hope that you'll carefully review how we went through this. Again, it took us a long time to describe how to break the vectors into components because we tried to explain each step very painstakingly. But I hope that you'll review this and practice this so that you can go through this process in a reasonable amount of time and with efficiency and confidence. So carefully study the process that we went through. I really took my time trying to explain these steps, but your goal is to get to the point where you feel that these steps are boringly easy. So if you were bored by that explanation that I just went through, that's great. The goal is to get to the point where breaking this vector into components is boringly easy. This isn't really supposed to be the hard part of physics. So you need to keep practicing this until you get to the point where this process is boringly easy. So the trickiest parts here are we need to remember that we're not going to draw the right triangle with horizontal and vertical legs. Don't draw the right triangle with horizontal and vertical legs. Draw the legs parallel to the axes. Then you have to use geometry to figure out the angles inside the right triangle. Then you label, then you decide which angle you're going to focus on. It's good to label that with an asterisk. Label hypotenuse, opposite, and adjacent side. Set up your SOH-CAH equations. So now let's take the numbers that we figured out and build them into our force table. W sub x is positive 50.6 newtons. And our W sub y that we determined was negative 72.2 newtons. Now again, one of the most common mistakes that students would make on this problem is forgetting the negative sign on W sub y. So make sure you're clear on why there's a negative sign on W sub y. There's a negative sign on W sub y because that y component is pointing opposite to our positive y-axis. W sub y is anti-parallel to the y-axis, and we explained how to figure out this, how to draw that component and figure out the arrows on that component. So make sure you're clear on how we ended up with that negative sign. That might seem like a minor detail, but that's crucial for getting the problem right. So now we're ready to move on to the normal force. We were not given a number for the normal force. Is there a special formula for the magnitude of the normal force? No, there's no special formula for determining the magnitude of the normal force. So all we have to do to handle that is just represent the magnitude of the normal force by this symbol, little n. We'll just represent the magnitude of the normal force by this symbol, little n. So remember, there's no special formula for the magnitude of the normal force. When you're dealing with a force that has no special formula for its magnitude, we just represent that magnitude with a symbol. And that's what we did here. And now we can break that normal force into components. Well, here we can use this rule. Our normal force is parallel to the y-axis, and that means that the y component of the normal force should have the same magnitude and direction as the overall normal force. Well, the overall normal force is pointing in our positive y direction. So n sub y has that same positive direction. And the magnitude of n sub y will be the same as the magnitude of the overall normal force, which we decided to simply represent by the symbol little n. So that's our y component, and now the component in this case for the other axis is 0. So n sub x will be 0. So it was straightforward to break this normal force into components. We didn't know a number for the normal force, but that did not prevent us from breaking it into components. We just used this symbol to help us represent the components. Now I hope you can see why we could not use this rule for the weight. We couldn't use this simple rule for the weight because the weight force is neither parallel nor anti-parallel to either of the axes. When a force is neither parallel nor anti-parallel to either axis, that's when you have to use the right triangle method. When the force is parallel or anti-parallel to an axis, like we had for the normal force, then you do not need to draw a right triangle. You can just use this simple rule. Notice that components are all about the axes. It's impossible to figure out the components correctly unless you're as clear as possible about which axes you're using. So make sure you actually write down the axes that you're using and keep consulting those axes when you're breaking vectors into components. Components are all about the axes. Components are a way of representing the forces or representing vectors relative to the axes. We finished our force table. Try to make your force tables as organized and neat as the force tables that I'm demonstrating in these videos. Try to use the exact same symbols that I'm using and the exact same notation that I'm using. Remember to put plus signs in front of your positive components because that will help you to remember the negative signs that you need in front of your negative components. Summary of how we attack the force table. If a force has a special formula, we use that special formula to represent the magnitude. That's what we did with the weight. If the force has no given value or special formula, you represent the magnitude by a symbol. That's what we did with the normal force. And remember, for purposes of the force table, do not try to figure out how the forces will interact with each other. The normal force on this problem will be affected by the weight. But we didn't try to figure out how the normal force will be affected by the weight. We just represented the magnitude of the normal force with the symbol little n, and we will let the Newton's second law equations later in our solution figure out for us how the normal force will be affected by the weight. So we've completed this step and this step for our force table. We're ready to move on to the next phase of our process, the Newton's second law equations, where we'll write these two equations at the top of two adjacent columns. Sigma f sub x equals ma sub x. Sigma f sub y equals ma sub y. Write these equations out using the exact correct symbols like I have them written here. All right, now remember, what does this sigma symbol mean? It means that we need to add all the x components of the forces, which in this case will be w sub x plus n sub x. W sub x and n sub x. And here the sigma tells us we need to add all the y components of the forces, which would give us w sub y plus n sub y. Now we can plug in the numbers and symbols from our force table. W sub x is 50.6 newtons. N sub x is 0. W sub y is negative 72.2 newtons. It's crucial to include that negative sign. N sub y is n. We'll leave out this extra plus just to make the math simpler. Now we can plug in on the right sides of our equations. So for the mass, we can plug in 9 kilograms. What can we plug in for a sub x? Well, we really don't know a sub x on this problem. And if we don't know something, we just have to represent it by a symbol. So we'll just continue to call that a sub x. Just like since we didn't know the magnitude of the normal force, we represented that by a symbol. We don't know a sub x, we represent that by a symbol. But we can do better with a sub y, because this object is moving down the inclined plane. This object is moving parallel to the x-axis. So this object is motionless in the y component. This object is motionless in the y component. There's no motion parallel or anti-parallel to the y-axis. The only motion is parallel to the x-axis, down the inclined plane. And if the object is motionless in the y component, that means that a sub y is 0. Why don't you pause the video and write out the steps of the logic for how we know that a sub y is 0. Here are the steps of the logic. We decided that the mass is motionless in the y component. That means that Vy is constant at 0, because the magnitude of Vy indicates the object's speed in the y component. Well, this object has no speed in the y component, so Vy is 0. Now the key is that Vy is constant. Just because Vy is 0, that does not mean Ay has to be 0. Acceleration doesn't have to be 0 when velocity is 0. But when velocity is constant, acceleration does have to be 0. We're using this rule here. Because Vy is constant, that means Ay is 0. That's why it's correct to plug in a 0 for this acceleration number, for a sub y. Could we plug in 0 for a sub x? Absolutely not, because the object is certainly not motionless in the x component, and there's no reason to think that the object is moving with constant speed in the x component. There's no reason to think that a sub x is 0. That's a great example of how you have to think about the components separately. Our analysis for a sub x is completely separate from our analysis for a sub y. By the way, this analysis helps us to see why these are good axes to pick. Notice that our analysis here depended on the axes. A sub y was 0 because we were motionless in our y component. But that's because we picked a y-axis that points in this direction, perpendicular to the inclined plane. So now you can see why these axes were good. These were good axes for us to pick for this inclined plane problem, because they allowed us to have one component where the object was motionless, and that allowed us to have one component where the acceleration was 0. If we had picked horizontal and vertical axes, then the object would be moving partially in both components, and as a result, we would have both components of acceleration would be non-zero. Neither acceleration component would be 0. So that's why horizontal and vertical axes would not work well here. So remember, the rule is it's a good idea to pick an axis that's parallel to the object's direction of motion. And now we can see part of the reason for that. When we picked the x-axis parallel to the object's motion, that allowed the object to be motionless in the y component. And that allowed a sub y to be 0. And clearly it's going to be easier to solve the problem when one of the components of the acceleration is 0. That simplifies things. To repeat, the analysis here illustrates why these were advantageous axes to pick for this inclined plane problem, because they allowed a sub y to be 0. You'll get that advantage automatically if you simply set one of your axes to point in the object's direction of motion. That's the rule that we've learned for choosing the axes. So as usual, I've been spelling out each step of the logic very slowly and painstakingly. I carefully spelled out how we knew that a sub y was 0. Obviously, you want to practice and think about these ideas so you get to the point where you can identify that a sub y is 0 much more quickly than the time it took me to talk through the logic. But the first few times that you put in a 0 acceleration component because an object is motionless in a component, it's good to actually think through the logic steps so that you understand what you're doing. So we've completed this step, we've completed this step, we've completed this step. Because the object was motionless in the y component, we knew that the y component of its acceleration would be 0. Okay, so now we need to use algebra to solve. Well, remember the question is asking us about the normal force, so it would be natural to start our work with the y equation, which has the symbol for normal force. And notice that this equation has only one unknown. Since there's only one unknown, we should be able to solve this equation for the unknown. The right-hand side simplifies to 0. This equation is very easy to solve by adding 72.2 to both sides. We're adding 72.2 to cancel the negative 72.2 on the left. Now we've solved to a single number, so we should put in the units. SI units for normal force are newtons, just like they are for any type of force. Notice that first we wrote the general equations, then we plugged in specific numbers and symbols. Kept all the versions of the y equation in this right-hand column to keep the math organized. Let's make some checks to see if this makes sense. Does the sign of this make sense? This came out positive. Does that make sense? Well, yes, because what does this symbol stand for? I hope you didn't say this symbol stands for the normal force. This is the complete normal force. This symbol just stands for the magnitude of the normal force. Magnitudes can't be negative, so it makes sense that this came out to be positive. Does the size of this answer make sense? Well, it's interesting to compare this to the magnitude of the weight. 72.2 newtons is less than 88.2 newtons. So we got that the magnitude of the normal force came out to be less than the magnitude of the weight. I encourage you to pause the video and try to figure out why that makes sense. You can use this version of our free body diagram to see why this makes sense. Notice that I'm just showing the components of the weight force. Remember, we already figured out that the y component is pointing in the negative y direction and the x component is pointing in the positive x direction. So I've drawn the directions of the x and y components of the weight to be consistent with the directions in our right triangle over here. Why does the normal force exist? Remember, the normal force exists to prevent the mass from being pulled through the surface from moving through the surface of the hill, of the inclined plane. Well, who is trying to pull the mass through that surface? It's the Earth's gravity. The Earth's gravity, the weight, is trying to pull the object into the inclined plane, but only the y component of the weight is trying to do that. Only the y component of the weight is trying to pull the object into the inclined plane. The x component of the weight is trying to pull the object down the inclined plane. Only w sub y is trying to pull the object into the inclined plane. So the normal force doesn't have to cancel out the entire weight. The normal force only has to cancel out the y component of the weight. And notice that, in fact, the magnitude of the normal force came out to equal the magnitude of the y component of the weight. The magnitude of our normal force, 72.2 newtons, equals the magnitude of the y component of the weight, which is also 72.2 newtons, just like we would expect from this version of the free body diagram. This version of the free body diagram suggests that the normal force has to equal w sub y in magnitude in order to cancel out w sub y, and that's the result that we got from our mathematics. So we're seeing that our result does make sense. So in fact, in this picture, I tried to draw this arrow to be about the same length as this arrow, because they should be canceling each other out. So you can see it does make sense that the normal force came out to be less than the weight, because the normal force only has to cancel the y component of the weight. Remember that this type of logic that we're going through, here we're thinking about the interactions between the forces. Remember that you should not think about those interactions when you're filling out your force table. Let the Newton's second law equations figure out the interactions for you, but then when you're finishing part of the problem, then that's a good time to think about whether the interactions make sense. Notice here that Newton's second law saw that the normal force was going to have to balance out the y component of the weight so that they would cancel out to zero, so that the object would not begin moving through the inclined plane. So Newton's second law correctly figured out for us those interactions, and now that we're finished with this part of the problem, we can see that those interactions do make sense. Notice how it helps to think in terms of components. To understand the interactions between the forces, it's much more helpful to focus on the components of the weight force rather than on the overall weight force. Okay, so we checked that the size of this answer does make sense. If the normal force had come out to be greater than 88.2 newtons, we would know we'd made a mistake, because that would actually not make sense on this problem. Okay, so I've written out the answer to the question. Did you notice I made a mistake? We have to include the units, or our answer is wrong. 72 newtons is the magnitude. I rounded this result off a little bit more for the final answer. We'd already figured out the direction of the normal force earlier in our work, perpendicular to and pointing away from the surface of the hill. So we completed this step of using algebra to solve. Check that you've answered the right question and that you've answered all parts of the question. So yes, we answered the magnitude and direction of the normal force. Make sure you answer all parts of the question. A lot of students might just say the answer to A is 72 newtons, and they might forget that the question's also asking for the direction of the normal force. So make that check that you answered all parts of the question, and we should notice that there's still another part of the question we haven't answered, part B. We've already checked that our answer makes sense. We made sure that we included units. This check is not relevant for this problem because this is for symbolic answers, and our answer was numeric. So now we have to move on to part B. Remember that for each question, you should try to write down a question mark that will help you, to represent the question. The question's asking for the magnitude of the acceleration. A good symbol for that is A without the arrow. A with the arrow represents the complete acceleration, including direction. Without the arrow, it represents just the magnitude. And we also want the direction. Of the acceleration vector. Here it makes sense to include an arrow because we want something with a direction. Always try to use the exact right symbol to help you represent what the question is asking for. So we went back and recompleted this step for part B, and now we're ready to move all the way down to algebra for part B, because we can reuse the setup that we've already done for part A. We'll use the same free body diagram and force table and equations for part B that we did for part A. Well, yes, in this case we can, because part B didn't give us any new information. Part B didn't give us any new information. It was really asking about the same situation as part A was. But that's something you always have to check. Sometimes on multi-part problems, your work for part A will not be completely relevant for part B. So you always have to check to see whether each new part of the problem introduces new information that would prevent you from reusing your old work. But here we can just reuse our old work. We're already done with the y equation for Newton's second law, so now we can work with the x equation. Notice that the x equation here deals with acceleration, a sub x, which should be helpful for finding the overall acceleration. So it's easy to simplify this equation. The left-hand side simplifies to 50.6 equals 9a sub x. That equation is easy to solve. We just divide both sides by 9 to get the a sub x by itself. We have to do the calculation 50.6 divided by 9. So that comes out to be 5.62. I guess I'll just round that off to 5.6. Now that we have a single number, we should put in the SI units, and you should have memorized that the SI units for acceleration are meters per second squared. We should check whether the sign and the size of this result makes sense, but I think I'll do a few more steps here and then come back to that issue. So let's just try to use this to answer the question now. Well, remember the question was asking us about what they call the acceleration, and the question implies that what they want is the magnitude and direction of the overall acceleration vector. What we have figured out here is the x component of the acceleration, but it should be pretty easy to go from the x component to the overall acceleration vector for this problem. So we need to use what we know about the components to answer the question about the overall acceleration. Well, we know that a sub x here is 5.6 meters per second squared. Let's go ahead and put in the sign. This number came out to be positive mathematically, and I recommend that you include plus signs in front of your positive components. So I'll put that plus sign in here. So our a sub x here is positive 5.6 meters per second squared. And didn't we already figure out a sub y is 0? We earlier determined that a sub y would be 0. We plugged that in here. So it should be easy to use those components to get some results for the overall acceleration. Here's the rule, which I think we already used earlier in this video. Since the acceleration has a 0 y component, we know that the overall acceleration has the same magnitude and direction as the x component. Well, a sub x is positive, so it's pointing in our positive x direction. So we can say that the direction of, and remember we're saying that because this component is 0, the direction of the overall vector is the same as the direction of the x component. That's pointing in the positive x direction. We can describe that as pointing down the inclined plane, parallel to and down the inclined plane. Our positive x direction points parallel to and down the inclined plane. So the overall vector has the same direction as the x component. Notice that we don't say over here that this direction is positive. We use positive and negative to describe the components. But here we'll use not a positive or a negative, we'll use words in this case to describe the direction of the overall vector. And again, because this component is 0, the magnitude of the overall vector is the same as the magnitude of the x component, which is our 5.6 meters per second squared. Magnitudes are never negative, so there's no need to emphasize that this magnitude is positive, so there's no need to put a plus sign in here. All right, so we used this idea that since the acceleration has a 0 y component, the magnitude and direction of the overall vector was the same as the magnitude and direction of the x component. Although, like I said, we described the direction here a little bit differently than we described it here by just using the plus sign. Okay, so we are able now to answer the question for part B. Here's our answer. Did you notice the big mistake that I made in this answer? This answer is wrong until we put in the units. You must include units on your answers. All right, now that's better. Make sure that you have the SI units for acceleration memorized so that you can supply those when needed. All right, now that we've answered part B, now would be a good time to step back and ask if the results for part B make sense. Let's begin by drawing this acceleration vector in our main sketch, parallel to and down the inclined plane. So here's that vector arrow pointing parallel to and down the inclined plane. Every vector arrow has to be labeled. And this one should be labeled as the acceleration vector. So let's stop and interpret this velocity and acceleration so we can see if this makes sense. How would you interpret this velocity and acceleration? Here's the rules. The direction of the velocity vector indicates the object's direction of movement. Since the velocity is pointing down the inclined plane, we know that the object is moving down the inclined plane. The object is moving down the inclined plane because of the velocity vector. Now remember that the direction of the acceleration vector does not indicate which way the object is moving. So how do we interpret this acceleration? We can interpret that acceleration using this rule. Because our acceleration and velocity are parallel. They point in the same direction, and that means the object is speeding up. Because of the velocity, we know the object is moving down the inclined plane. Because the acceleration is parallel to the velocity, we know the object is speeding up, moving with increasing speed. Now we should ask if these results make sense. Do these results make sense? Are they consistent with the forces on this problem? You might want to pause the video and try to figure out for yourself if these results are consistent with the forces for this problem. Well, it seems that this object was already sliding down the hill when the problem began. So when the problem began, the object was already in motion. And according to Newton's first law, once an object is already in motion, it has a natural tendency to continue moving in a straight line in that same direction at constant speed. So we don't need to explain why the object is moving down the inclined plane, because that started before the problem began. But remember that the natural tendency for an object in motion is to move at constant speed. So we do have to explain why the object is speeding up. There must be some force that explains why this object is speeding up. We don't need to explain the velocity, but we do need to explain this acceleration. Well, that should be very easy to explain. What's the force that explains this acceleration down the inclined plane? Clearly, that's W sub x. Remember, this is the version of the free body diagram where we've already split the weight force into its components. This is most useful for thinking about the relationships between our forces. Okay. So W sub x is the force that explains why W sub x is pulling down the inclined plane, and that explains why we have an acceleration down the inclined plane. So W sub x is the force that explains why the object is speeding up. So now we can see that it makes good sense that A sub x came out to be positive. Remember, we should always think about the sign of our results and ask if that makes sense. It makes good sense that A sub x came out to be positive. The x component of the acceleration is in the positive x direction because W sub x is pulling in the positive x direction. If this acceleration had come out to be negative, if A sub x had come out to be negative, we would have known we had made a mistake. It wouldn't make sense for A sub x to be negative because there are no forces pulling in the negative x direction. So now we've checked and we've seen that the positive sign on this result does make sense. The positive value for A sub x is explained because W sub x is pulling in the positive x direction. So we've seen that the sign of this result makes sense. What about the size of this result? Is there anything that we can compare A sub x to see whether the size of this result makes sense? And in this case, there definitely is. We can compare A sub x 5.6 meters per second squared. We can compare that to 9.8 meters per second squared. You can see that 5.6 is less than the 9.8 meters per second squared, and that means that the magnitude of A sub x came out to be less than little g. I'm calling this a magnitude because now we're just focusing on the size and not focusing on the plus sign. So this number came out to be less than little g. Does that make sense? Why don't you pause the video and try to figure out why it makes sense that this number is less than little g? Well, that does make sense. Remember that little g is the magnitude of free fall acceleration. Little g is your acceleration when the only force on the object is the force of the Earth's gravity. So little g is caused by, so little g is the acceleration when the only force on the object is the weight force. Little g is the acceleration caused by the weight force. Little g is the magnitude of the acceleration that would apply for a projectile motion problem, that is, or a free fall problem. That is, little g is the magnitude of the acceleration that would be caused just by the force of the Earth's gravity. That is, little g is the magnitude of the acceleration that would be caused by the full force of the object's weight. Little g is the magnitude of the acceleration that would be caused by the full force of the object's weight, which occurs in projectile motion. But notice that in our problem, the acceleration is coming only from the x component of the weight. Since only the x component of the weight is causing acceleration here, the magnitude of the acceleration came out to be less than what the acceleration would be if it was caused by the full force of the weight. Remember that in our problem, the y component of the weight is getting canceled out by the normal force. In our problem, the y component of the weight is being canceled out by the normal force, and that leaves only the x component to cause the acceleration. Since this acceleration is being caused by only a component of the weight force, it comes out to be less in magnitude than little g. Little g is the magnitude of the acceleration that you would get for a projectile motion problem where the acceleration was being caused by the full weight force. So I hope that you're seeing that what I wrote down over here is what the free body diagram would look like for a projectile motion problem, so that we can compare that with what the free body diagram looked like for this inclined plane problem. That way we can compare what the magnitude of the acceleration should be in a projectile motion problem, little g, with what the magnitude of the acceleration should be in this particular problem that we were working on. Less in magnitude than little g. The acceleration on our problem came out to be less in magnitude than little g, because in our problem the acceleration is being caused only by w sub x, only by the x component of the weight, whereas little g is the acceleration that you would get on a problem where the acceleration was being caused by the full force of the object's weight. On our problem, the y component of the weight is being canceled out by the normal force, and that leaves only the x component of the weight to cause the acceleration. Notice that in a projectile motion problem, there would be no normal force to cancel out a portion of the weight. There's no normal force in projectile motion problems because by definition, projectile motion is when the only force on the object is the force of the weight, the force of the Earth's gravity. Projectile motion occurs when there's nothing touching the object, and therefore in projectile motion there's no surface to exert a normal force on the object. And therefore in projectile motion there's no force to cancel out a portion of the weight. We can also say that the result we got on this problem matches, I think, what our intuitive prediction would have been if we hadn't studied any physics at all. If you dropped one object in free fall and you let another object slide down an inclined plane, I think your intuitive prediction, even without having studied any physics, is that an object that's just dropped in free fall will accelerate faster and fall faster than an object that is sliding down an inclined plane. Even if the inclined plane was frictionless, even if there's no friction on the inclined plane, our common sense prediction from everyday experience, I think, so for example, even if the inclined plane was extremely slippery ice, even if the inclined plane was made of extremely slippery ice with almost no friction, I think we would still expect in everyday experience that an object that is sliding down an icy, frictionless inclined plane is going to accelerate slower and slide more slowly than an object that we simply drop straight down in free fall. That's the common sense expectation we would have even if we hadn't studied any physics at all. And again, our results match that intuitive prediction, that the acceleration down the inclined plane is less than the acceleration would have been if the object was just dropping in free fall. That would have been our intuitive prediction without studying any physics at all. And now hopefully that we've seen the physics, we can have a deeper understanding of why an object would slide down an inclined plane more slowly than it would fall if it was dropped in free fall. It's because the free fall acceleration is caused by the full force of the object's weight, whereas when an object is sliding down an inclined plane, the y component of its weight is canceled out by the normal force, and the acceleration then is caused only by the x component of the weight. The physics that we've studied helps to explain our everyday experience that an object that's falling straight down through the air falls more quickly than an object that's sliding down an inclined plane. Even in the case of a very slippery inclined plane that might have no friction. Even in the absence of friction, an object would slide down an inclined plane more slowly with less acceleration than it would fall if it was just dropped straight down. So we've checked that both the size and the sign of this answer make sense. I know that some of those checks are challenging and subtle and difficult to think through, but I encourage you to practice that thought process. The more you practice that, the better you'll get, and it'll give you a chance to catch your mistakes sometimes when you make them. So I'll make a check mark to show that we checked that this does make sense on this problem. Okay, so we've checked that this answer makes sense. For completeness, we can finish up by talking about the roles of all of these different forces. What's the role of W sub x? W sub x is causing this acceleration down the inclined plane. What's the role of W sub y? W sub y is attempting to begin dragging the mass down into the surface of the inclined plane. W sub y is trying to drag the mass into the surface of the inclined plane, dragging in this direction, but W sub y is going to fail at that because it's going to be canceled out by the normal force. All right, so now we've completely explained all the interrelationships and interactions between all these forces and how they're reflected in the velocity and acceleration. Remember that that thought process I just went through, that whole thought process is something you should save for the end of the problem. When we're first filling out the free body diagram and when we're filling out the force table, we do not try to figure out how the forces will interact with each other. Instead, we just consider each force on its own terms just to avoid confusion. We didn't try to figure out how the normal force would interact with the weight force or affect the motion of the object. We just symbolized it by the symbol little n in our force table. Otherwise, we could get confused. Remember that we let the Newton's second law equations figure out the interactions for us. The y equation figured out that the normal force has to balance W sub y to cancel out to 0 so that the object won't get dragged through the surface of the inclined plane. And the x version of Newton's second law saw that since W sub x is pulling in the positive x direction, A sub x is going to come out to be an acceleration in the positive x direction. The Newton's second law equations figured out the relationships between the forces and how they were going to affect the object's motion for us. We didn't have to figure that out on our own. That would be too confusing. But again, once we had finished the problem and once we've gotten our results, that's an excellent time to step back. And at that point, that's a good time to step back and to indeed think about the relationships between the forces and the motion to build and deepen our physics insight and to check whether our results make sense, which gives us a chance to catch any mistakes that we might have made. So we've completed the Newton's second law phase for part B of the problem. We used algebra to solve for the unknown in the x equation for Newton's second law, and then when we got an answer, we checked that we answered the right question and checked that we answered all parts of the question. Did we do that check? Let's do that now. The problem asked for the magnitude and direction of the acceleration, so make sure that you answer all parts of the question. You make sure, don't just give the magnitude, make sure that you're also giving the direction. And we can see that now we're finishing the problem because there's no part C. All right, so now we've checked that we answered the right question and all parts of the question. We've checked that our answer makes sense. I think we checked that we included units in our answer. This check is not relevant because this is for symbolic answers and our answer is numeric. Get in the habit of making these checks. Now we need to review this question and to review what we learned in our solution of this problem. Well, the big difference between this problem and the earlier ones in this series is that this is the first inclined plane problem that we've worked on together. So what have we learned about inclined plane problems? Well, the most important thing that I hope that you'll agree with is that even though this was an inclined plane problem, we still used the same systematic process for this problem that we would for other Newton's second law problems. Inclined plane problems can be attacked using the same systematic Newton's second law method that we've used for other problems. I hope that you would agree with that. So remember, we should not think of this, in a way, we should not think that we were not using an inclined plane problem-solving framework. Inclined plane problems is not a problem-solving framework in physics because we've seen here that inclined planes are just an application of the Newton's second law framework. So the big lesson is that we don't need to learn a big new approach for inclined plane problems. We simply apply the same Newton's second law approach that we would for any other Newton's second law problem. Now, of course, there are details there that we have to pay attention to. How do we adapt that method for inclined planes? So one thing we saw, for example, is there's many things that don't change at all for an inclined plane. The direction of the weight for an inclined plane is still down. That's the general rule. The magnitude of the weight is still mg. That's the general rule. The direction of the normal force is still perpendicular to and away from the surface. But that gives us a different direction for the normal force than we would if we had a horizontal surface. So I hope you understood how we got this direction for the normal force. Well, the big difference here was that it took more work to break the weight into components. And that's the part of the problem that gives most students the most difficulty, how we broke the weight into components. Let's one more time review the steps for that. Of course, first we used mg to find the magnitude of the overall weight. All right, then the first thing that people have trouble with is drawing the right triangle for the weight vector. Remember, the reason we have to draw a right triangle is because the weight vector is neither parallel nor anti-parallel to either axis. So we have to use the right triangle method. Students tend to have difficulty drawing these right triangles because they try to draw the right triangles with horizontal and vertical sides. So remember the correct rule. The sides of the right triangle, the legs of the right triangle, should be parallel to your axes. Drawing the right triangle is all, figuring out components is all about the axes. So I hope you understood how we came up with these right triangles. You could have used either of these two right triangles in your solution. Remember, it's also very important to get the right directions for the legs of the right triangles. So if necessary, review how we figured out the directions of these components. Those directions were important because without the directions, we wouldn't be able to figure out the plus or minus signs on the components. And those plus and minus signs were crucial. Okay. And then the next problem is a lot of students try to use this angle for SOH CAH TOA. But I hope you can agree now that this angle is not used. We can't use this angle for SOH CAH TOA. We need to know an angle inside the right triangle. So we have to use high school geometry facts to figure out at least one of the angles inside the right triangle. So you can go back and, if necessary, review the geometry we went through to figure out the angles. Again, for a real problem, you would only have to either figure out the angles for this triangle or for this triangle. You wouldn't have to do both. We just covered both for completeness. All right, and then once we had those angles, then we were ready to label opposite, hypotenuse, and adjacent sides and use SOH CAH TOA. And remember, you should figure out which angle you're focusing on. Notice how we put in an asterisk here to show which angle in the triangle we're focusing on. It's conventional to focus on the 35-degree angle rather than the 55-degree angle because 35 degrees matches the angle that we were given. And then we set up the SOH CAH TOA equations, and the SOH CAH TOA equations told us that in this particular case, we would use cosine for the y component and sine for the x component. The way to break the weight into components is to go through that series of steps. Now, of course, eventually you'll probably get to the point where you don't need to write all of these steps down, and that's okay. If you get to the point where you're getting the problems right without writing all these steps down, that's fine. But you need to know how to write each of these steps out. And if you see a problem that seems a little bit different than the problems you've dealt with before, the only way to decide how it's different and how you need to adapt is, again, by writing out these steps. So for right now, I would encourage you to write out all or a lot of these steps. And even when you start cutting back on how many steps you're writing down, you need to be aware of them in your head so that you can still use them for problems where you need to adjust your approach a little bit. All right, and then also remember, one of the biggest mistakes that students would make on this problem, even if they got the correct components, is that they might forget this negative sign on W sub y. So remember to put a plus sign in front of your positive components, and that will help you to remember to put the very crucial negative sign in front of your negative components. So the main new issue for inclined plane problems is that it takes more work to break the weight into components. Inclined plane problems are very similar to other Newton's second law problems. The big new issue is that it just takes more work to break the weight into components. And we took our time and really tried to explain each of those steps. So hopefully you'll feel that you've made some progress on that. If you're comfortable breaking the weight into components for an inclined plane problem, then other than that, an inclined plane problem should be no more difficult than any other Newton's second law problem. As usual, I'll remind you that you should be trying to make your scratch work look like my scratch work. Try to use the same notation and approach in your own work that I'm using. A nice clean free body diagram, a nice clean organized force table, nice clean math for your Newton's second law equations. Remember to try to set the Newton's second law equations up in two side-by-side columns. The left-hand column for versions of the x equation, the right-hand column for versions of the y equation. That's the way to keep your math organized. And for now, I would recommend that you try writing out a lot of these steps for breaking the weight vector into components as well, imitating the notation that I used. Eventually, I know that you'll probably want to skip some of these steps, but for at least a few more problems, you should be writing out these steps so you build your understanding and comprehension of the method so that you can adapt to problems that are a little bit different than this one. So study the notation and approach that I used for breaking the weight into components, and I encourage you to imitate that notation. Here's a few more principles that you should try to make sure that you're using on each question. To succeed in physics, think in terms of components. One thing we saw here is that components are about the axes. So the big new thing for an inclined plane problem is that we use slanted axes. For an inclined plane problem, we use slanted axes, and the axes determine your components, so that's going to affect what your components look like. So focus on your axes. That's a part of thinking in terms of components. We've just been talking about how crucial it was to get the correct components for the weight. So notice that in this problem, the overall magnitude of the weight was 88.2 newtons. Where did we plug the 88.2 newtons? Where did we plug that weight into the Newton's second law equations? Answer, we didn't. We never plugged 88.2 newtons into the Newton's second law equations. We only broke the components in. Here we plugged in the x component, and here we plugged in the y component. That's a great example of how we need to think in terms of components. The components of the weight were much more useful to us than the overall magnitude of the weight. Of course, we didn't ignore the overall magnitude of the weight, but we used it to find the components. So notice, where did we plug this number, the mg number? Where did we plug the mg number into our Newton's second law equations? We didn't. We just used this number to find the components, and then we plugged the components into the equations. That's a great example of how we have to think in terms of components. Another great example is the difference between how we treated a sub x and a sub y. A sub y was 0 because the object was motionless in the y component. A sub x was certainly not 0. So we had to treat those two components completely separately and think about them separately. So that's a great example again of how it was crucial here to think in terms of components. Always try to use the exact right symbols, including the exact right subscripts. So be tough on yourself there. Take a look at your own scratch work and just check if you're using the same exact symbols in your scratch work that I'm using. Be tough on yourself, and the payoff from that will be, as you get better at using the exact right symbols, your physics skills will develop and deepen, and you'll be able to attack harder and harder questions. One of the most common mistakes students make, and one of the most common things that holds people back in physics, is confusing the different concepts, having the concepts blur together. And a great way to fight against that is always labeling things with the exact right symbol. That will help you to be as clear as possible about what concept you're thinking about. So make sure you're using the same symbols in your force table that I'm using, for example. Try to make sure you're using the same symbols in your Newton's second law equations that I'm using. I encourage you to use the same symbols when you're doing your SOH CAH TOA work for breaking things into components that I'm using. Those symbols are all the symbols that are chosen to be the most useful for a beginner to develop their physics skills. So be tough on yourself and try to force yourself to use the exact right symbols, including the exact right subscripts. Don't use the word it. Always give things a label. So don't say that it is 88.2 newtons. Say that the overall magnitude of the weight is 88.2 newtons. That might remind you that you still need to break that into components before you can plug that into your equations. Don't say that it is 0. Say that a sub y is 0. That might remind you that the analysis for a sub x is completely different from the analysis for a sub y. Force yourself to use a name or a symbol for each concept that you're thinking about, and again, that will gradually help you to deepen and develop your physics skills. On this problem, all of these numbers represented aspects of the weight. So we need to use the right label so that we can see the difference between them. It doesn't help to say that it's 88.2 or it's negative 72.2. What's helpful is to say that the overall magnitude of the weight is 88.2 newtons. It's helpful to say the x component of the weight is positive 50.6 newtons and the y component is negative 72.2 newtons. Or maybe it's easier just to use the right symbols. W sub x is positive 50.6 newtons. W sub y is negative 72.2 newtons. By forcing yourself to give the exact right label or name or symbol, you're preventing these different numbers from blurring together in your head, and you're more likely to plug them in the correct places into your equations. If this problem was extremely challenging for you and you didn't really quite know how to attack it, then I would recommend that a good thing to do now would be just to redo this same problem. Just redo this problem from scratch to make sure that you've internalized the techniques that we've been talking about here. Ultimately, your goal is to get to the point where it's boringly easy. This problem is boringly easy. You want to get to the point where this problem is boringly easy and where it's boringly easy to break the weight into components, which was the biggest issue on this problem. It should be boringly easy for you to break this weight into components, but that takes practice. So if this was a very challenging question, it would be good just to try it again to make sure you've internalized the techniques. When you feel you have internalized the techniques from this problem, you can go on and try the next problem in this video series. You can find that next problem in the next video, or of course you can consult the next problem in the problems document. And when you're doing those next problems, I hope that you'll be trying to practice and use the skills and techniques and notation that we demonstrated in this problem in this video. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.